All right, so now we'll take a look at finding the slope of a tangent line using the difference quotient. Um, so what we want to do is we want to have our point of tangency's x value. We're going to define the point of tangency's x value as just x. But I know that this point here, which is the point x f of x comma f of x, I know that that is my point of tangency. So what I'm going to do is pretty much the same thing I've been doing. I'm going to create another point and have that other point move closer and closer and closer to my point of tangency. So that second point, I'm going to call the x value of that second point x2, x with a little subscript 2. And this point here that has an x value of x2, I'm going to allow that point to get arbitrarily close to the point of tangency. So I'm going to have this point move closer and closer and closer and closer to this point. But before I do that, I want to define something here because I don't want x2 to appear in my formula. So I'm going to define delta x. I'm going to say that delta x is equal to x2 minus x. Delta x is just the difference between the two x values. The difference between the two x values. Here's something I want you to notice. I want you to notice that as x2 approaches x, as these two things get closer and closer together, so as x2 approaches x, it also means that delta x is getting smaller and smaller and smaller, or delta x is approaching 0. So as these two x values become arbitrarily close to each other, as x2 gets closer to x1, then their difference gets closer and closer and closer to 0. I want you to keep that in mind, all right? The other thing I want you to keep in mind is that if we solve this equation for x2, it turns out this equation here I'm talking about, it turns out that x2 is actually equal to x plus delta x, okay? So remember, I don't want x2 to appear in my formula. The second ordered pair here would be x2 comma the f of x2. But once again, I don't want to call it x2, so I'm going to replace x2 and f of x2 with what they equal, which is x2 is actually x plus delta x. So x2 is x plus delta x. And the other coordinate in the ordered pair would be the f of x plus delta x. So here, I'm not going to use this form of the ordered pairs representation because I don't want to use x2, but this represents the same thing because x2 is in fact x plus delta x from this definition up here. Okay, so let's go ahead and find the slope of the tangent line here. Well, the slope of the tangent line involves a limit. I'm going to do this. I'm going to take the limit, and usually we take the limit as x2 got closer to x. But x2 approaching x is the same as delta x approaching 0. So I'm actually going to take the limit as delta x approaches 0 of, then I'm going to take the y value here, this y value right here, or the f of x plus delta x, and I'm going to subtract from it this y value here, the f of x, and I'm going to divide that by this x value, which is actually x plus delta x, minus this x value, which is only x. I see here that those x's just cancel out, and I'm left with this formula for calculating the slope of a tangent line. The limit as delta x approaches 0 of the f of x plus delta x minus the f of x, all divided by delta x. You might recognize this without the limit is just the difference quotient. So this part right here, if you ignore the limit, this part right here is the difference quotient. So basically, what we're doing is we're taking the difference quotient and we're allowing delta x to tend towards 0. All right, let's look at what this looks like in practice. All right, so here is a function, the squaring function. And what I want, it says given the squaring function, I want to find the limit as delta x approaches 0 of the f of x plus delta x minus the f of x over delta x. We know this now, based on our previous discussion, to be the slope of a tangent line. So let's go ahead and find the slope of the tangent line using the difference quotient there. All right, so the first thing, well, we're going to take the limit as delta x goes to 0, but I need to find the f of x plus delta x. Well, the f of x plus delta x is what I get when I plug x plus delta x into the function. So that's going to be x plus delta x squared. Then I'll have minus, because here's the minus sign, right? Here's the minus sign right here. So minus the f of x. Well, the f of x is just x squared, and this is all divided by delta x. All right. Well, let's see. Let's simplify this a little bit. So the limit as delta x approaches 0, and x plus delta x squared gives me x squared plus 2x delta x plus delta x squared. And I still have the minus x squared in the numerator there also. And this is all still divided by delta x. So I have x squared and I have minus x squared. Those just cancel each other out. So I'll have the limit as delta x approaches 0 of 2x delta x plus delta x squared all divided by delta x. And what I want to do is I want to directly substitute 0 in to see if I can come up with this limit. So I'm going to substitute 0 in for delta x. So if you plug in 0 for delta x here, this term becomes 0. Plug in 0 for delta x here, this also becomes 0. 0 plus 0 is 0. So the numerator is 0. And the denominator, when you replace delta x with 0, is also 0. So I get this indeterminate form. Well, when you get the indeterminate form, you're either going to factor or rationalize or simplify the complex fraction. In this case, it's a polynomial, so we are going to factor. The factor that we're going to take out, there's a common factor of delta x in the numerator. So I factor out delta x, and I'm going to be left with 2x plus delta x, in which case I see that the delta x in the numerator and denominator just cancel each other out. And I'll have the limit as delta x approaches 0 of 2x plus delta x. And now I'm going to try to directly substitute again, and I get that this limit is equal to 2x. So the slope of the tangent line to a curve at the point where x is whatever the x value is just 2 times that x value. So the slope of the tangent line to the squaring function at any x value is 2 times the value of the x value. Okay, let's take a look at a second example here. So once again, we're taking the limit of the difference quotient as delta x approaches 0. This is how we're going to find the slope of a tangent line. The tangent line in this case is the line tangent to the square root function as opposed to the squaring function. So I'm going from this polynomial function, the squaring function, to this radical function, the square root function. Let's go ahead. So I'm looking for the limit as delta x approaches 0 of the f of x plus delta x. Well, that's going to be the square root of x plus delta x, or what I get when I replace the x in this function with x plus delta x. Minus, still minus, the f of x, the f of x. Well, this is the f of x, the square root of x, and that's all divided by delta x. So the only thing I really had to do was put the f of x plus delta x in here. The f of x is given, and delta x is in the formula. So then I want to calculate this limit. So I'll plug in 0 for delta x. But when I do that, I get the square root of x minus the square root of x, which is 0 over delta x, which is going to 0. So I once again get the indeterminate form. Well, in this case, we're not going to factor, we're going to rationalize. So let's rationalize the numerator here. Limit as delta x approaches 0 of the square root of x plus delta x minus the square root of x divided by delta x. And in order to rationalize this, what we want to do is we want to multiply the top and the bottom of the fraction by the conjugate of the square root of x plus delta x minus the square root of x. And that conjugate is the square root of x plus delta x plus the square root of x. I just changed the sign in between the two terms. And I multiplied the denominator by the same thing because if I multiply by 1, I won't change the actual value. And that's what this amounts to, multiplication by 1. Numerator and denominator are the same. This fraction is equal to 1. Okay, so here's something that you wouldn't know until you've gone through this a few times. When you're doing this kind of calculation, you multiply out the top, but you don't multiply out the bottom. You leave the bottom in factored form so that you can cancel the factor that's creating the 0 over 0 situation. So let's multiply out the top. The square root of x plus delta x times the square root of x plus delta x is x plus delta x. The two middle terms will cancel because the square root of x plus delta x times the square root of x is the exact opposite of the square root of x plus delta x times the negative square root of x. One will be positive, the other one will be negative, so they'll cancel. Outside, inside, cancel. So I do last, which is negative square root of x times positive square root of x, or minus x. In the denominator, remember I said don't multiply out the denominator, so I'm going to leave the delta x multiplied by the square root of x plus delta x plus the square root of x. Okay, so I have an x minus x here, and this leads to the limit as delta x approaches 0 of delta x over delta x times the square root of x plus delta x plus the square root of x. So I see here that I have a common factor of delta x in the numerator and in the denominator. Those cancel. And I'll have the limit as delta x approaches 0 of 1 over the square root of x plus delta x plus the square root of x. And now I'm ready to directly substitute again. If I directly substitute in 0 for delta x, I get 1 over the square root of x plus the square root of x, which is 2 square roots of x. So if I want the slope of the line tangent to the graph of 1 or of the square root of x at any x value, all I have to do is take that x value and plug it into this expression, and I'll get the slope of the tangent line. Let's do one more. So we've done a polynomial function, we've done a radical function, and now here's a rational function. A rational function, okay? So let's go ahead and calculate this thing. It's going to be, once again, the limit as delta x approaches 0 of the f of x plus delta x. Well, that's what I get when I plug x plus delta x into this thing for x. So I'll get 1 over x plus delta x. Then minus the f of x, which is 1 over x. And this is all divided by delta x. Okay, direct substitution. If I plug in 0 for delta x, this is 1 over x minus 1 over x, which is a 0 for the numerator, divided by delta x, which would make a 0 for the denominator. Once again, the indeterminate form. So we've already seen an example of factoring when we get the indeterminate form, rationalizing when we get the indeterminate form. This is the case where we're going to simplify this complex fraction. In order to simplify the complex fraction, I need to find the least common denominator for those two fractions in the numerator. So I look at the denominator of this fraction, and it has a factor of x plus delta x. That factor has to be included in the common denominator. The other fraction has a factor of x. that factor also needs to be included in the common denominator, so that the common denominator is actually x times x plus delta x, which is just the product of those two denominators in the numerator of that fraction, of that complex fraction. So I have the delta x that's still in the bottom down here, right? I'm going to combine these two fractions. Well, the LCD is this, so I'll keep that denominator, x times x plus delta x. And now let's take care of the numerators. Well, this first numerator was from a fraction that was missing the factor of x. So I'd multiply the top and the bottom of this fraction by x, leaving the numerator to be x times 1, which is just x. Then I have a minus sign, minus sign. And this fraction here is missing the factor x plus delta x that's in the LCD. So I'm going to multiply this fraction's numerator and denominator by x plus delta x. That's how I get the common denominator. But the numerator would then be 1 times x plus delta x, or x plus delta x. So I get this, and I'll have this is the limit as delta x approaches 0 of x, and I'm going to distribute that negative, minus x minus delta x, all divided by x times x plus delta x, and still divided on the bottom by delta x itself. Those cancel out. Those cancel. Also, this fraction here is delta x over 1. So I have a fraction here on top divided by this fraction, delta x over 1. I'm going to take this fraction here, delta x over 1, flip it, and multiply. So I'm going to get this, the limit as delta x approaches 0. I'm going to write the top fraction, which is negative delta x divided by x times x plus delta x. And then I'm going to multiply by the reciprocal of the denominator here, which is 1 over delta x. Well, some things happen here. I see here that I have a delta x up here and a delta x down here that just cancel each other out. So I'm calculating the limit as delta x approaches 0 of, this is negative 1 divided by x times x plus delta x. And now I can do direct substitution again. When I plug in 0 for delta x here, I get that this limit is equal to negative 1 over x times x, or x squared. So that would be the slope of a tangent line to the function at any x value.